So a pretty cool consequence of trigonometric angles is that I can assign a trig function. In fact, I can assign all 6 trig functions to any point on the Cartesian plane. So suppose I choose the point 3, 4. I can construct an angle, a trig angle, with the initial ray on the x-axis, the terminal ray coinciding with the point, and the vertex of the angle at the origin. So I'm looking at an angle theta for the point 3, 4. So all I need now is a right triangle. Well, if I were to construct a line straight down from my point to the x-axis, in fact, I would do that from anywhere. If I were in the third quadrant, I would take my line straight up to the x-axis, and my right angle would be along the x-axis on the negative side. But in this case, I'm in the first quadrant. So if I construct this right triangle, now all I have to do is figure out the value for the opposite side, because the opposite of theta, obviously, straight across, the adjacent side, and the hypotenuse. Well, the opposite and adjacent, super duper easy. The opposite side is just whatever my y ordinate is. So the opposite side equals 4. And my adjacent side is whatever my x ordinate is, which is 3. And then the hypotenuse, I have to use the Pythagorean theorem. So I have c squared, my hypotenuse is c, equals the square root. Well, c squared equals a squared plus b squared. So c equals a squared, so let's say 4 squared, plus b squared, 3 squared. So I'm looking at the square root of 16 plus 9, which is 25. And so c, or my hypotenuse, equals 5. Now I can assign trig functions. I can say that sine of theta, which is equal to the opposite over my hypotenuse. Although now that we're dealing in trig functions, we don't have to use opposite and hypotenuse anymore, because our angles are very firmly attached to the Cartesian plane. I can say that the sine is the opposite, or the y ordinate, over the radius, or the hypotenuse, which is the radius of the circle. So in this case, I'm looking at the sine of theta is 4 over 5. The cosine of theta, adjacent over hypotenuse. And so the adjacent in this case is the x ordinate, over the hypotenuse is the radius, over r. And so that is 3/5. And the tangent of theta, which is the opposite over the adjacent, in this case the opposite is 4 and the adjacent is 3. I'm sorry. In this case the opposite is y, and the adjacent is x, and specifically that would be 4/3. And so my inverse functions then would be the cosecant of theta equals the inverse, 5/4. The secant of theta is the inverse of cosine, 5/3. And the cotangent of theta is the inverse of tan, 3/4. So let's do an example of another quadrant. We want to find the 6 trig functions for -4, 3. So if I were to construct angles, the angle theta, the angle I'm looking at, is the angle used to create or to intercept that point. But my trig functions, and this is super important, my trig functions stem from creating a right triangle with the x-axis. So my values have to be related to the right angle associated with the x-axis. So theta remains in the same position, but as I evaluate it, I'm going to create a right angle with the x-axis. So in this case, sine of theta, and we don't have to use opposite over hypotenuse anymore. We can say the sine of theta is y over r, and in this case, y equals y equals positive 3 over, I don't know what r is. Well, I kind of do know what r is because my first point was 3, 4. A and b was 4 squared plus 3 squared. In this case, 4 is negative, but when I square a negative number, I'm just going to get 25. So I'm actually going to get that my hypotenuse or my radius equals 5 again. So my radius is 5. But there's a slight difference, so you might think that I would just go and use all the same sine function or trig functions as for this first angle, but I wouldn't because the sign of my ordinance matter. And you'll see that right here in the cos theta. Cosine of theta is x over r. Well, we know what r is, it's 5. But x in this case is negative 4. So the sign, S-I-G-N, matters when we're dealing with trig functions. If this were a geometry angle, we would never worry about there being a negative value because we would never have a negative value on a distance, on a measure of distance. But trigonometry puts our angles on a Cartesian plane, and so we do have negative and positive values. So tan theta then, which is y over x, is 3 over 5. Cosecant theta then would be the inverse, 5/3. Secant theta, the inverse, negative 5/4. And cotan theta, the inverse of tan theta, 5/3. So this is how we would find the trig ratios for any point on the Cartesian plane or almost any point on the Cartesian plane. There are points associated with quadrantial angles, QUAD, RANTAL. And basically these are angles that coincide with the axes. So let's sketch them in. Like any other angle, they have an initial ray at the positive x-axis. They have a vertex at the origin, but the terminal ray is aligned with one of the axes. So the positive, the terminal ray for a 90-degree angle aligns with the positive y-axis. The terminal ray for a 180-degree angle aligns with the negative x-axis. And the terminal ray for a 270-degree angle aligns with the negative y-axis. And the terminal ray, they're coterminal, the terminal ray for the 0 angle and the terminal ray for the 360-degree angle, they coincide, they're coincident angles, aligns with the positive x-axis. So this is 0 or 360. And I see that I missketched the 270. 270 would be the angle that carves through three quadrants and ends up on the negative y-axis. So what would the trig values for each of these be? If a point lays on, for example, somewhere on the positive y-axis, what would the 6 trig functions be? Well, the ordinate for the coordinate for that point would be x equals 0, y equals whatever r is. And so trig functions would be sine of 90 degrees, y over r, but y is r over r, so the sine of 90 is 1. Cosine of 90 is x over r, so that's 0 over r equals 0. Tangent of 90, y over x, so r over 0, undefined. The inverse is the same. Cosecant of 90 degrees would be 1, because the inverse of 1 is just 1. The secant of 90 degrees would be r over 0, undefined. And the cotangent of 90 degrees would be 0 over r, totally allowed, which equals 0. So they have various combinations. For quadrantial angles, have various combinations of 1, 0, and undefined. I'll do the third quadrant for 270 degrees. The sine of 270. Well, first I need to know what x and y and r are. So if I had a point that fell on the negative y-axis, the coordinate for that point would be x is 0. Oh, let's not do 270. Well, I'll give you the point. X is 0, and y again is r. But in this case, it would be negative r. Whatever the length of r is would coincide on the negative y-axis at negative r. So sine of 270, I think I will do it after all, is y over r, so r over negative r, negative 1. Cosine of 270, x over r, 0 over r, 0. Tan of 270 is y over x, negative r, over 0, undefined. And then the inverses would be negative 1, undefined, and 0. Let's do the sine of 180. So a point on the negative x-axis would have the coordinate, whatever r is, only it'd be negative. The distance on the x-axis would be negative r, and y would be 0. So 0 over r equals negative 0, which is just 0. Cosine of 180 would be x over r, negative r over r, negative 1. Tangent of 180 is y over x, 0 over negative r, equals 0. And then the inverse functions would be the same. I'm not going to do 360. You could certainly do it. What would the coordinates for a point on the positive x-axis be? Well, the distance along x would be positive whatever the radius is, and the elevation up or down is 0. And you would go through the exact same process. The only thing to notice is that the sine of 0 is exactly the same thing as the sine of 360. And I'll go ahead and do that one. Well, the sine is y over r. So in this case, y is 0 and r is r. So it would equal 0. Let's do a couple of examples of these. So let's find the exact value of the cosine of pi if r equals 1. So we're going to use the unit circle where the radius equals 1. So if I sketch that in real quick, I know that pi is 180 degrees over here. And if r equals 1, then the point that we're going to use to create our function, or to evaluate the cosine function, would be negative 1 for x and 0 for y. And so the cosine of pi is equal to y over r, excuse me, that's not correct, x over r and x is -1, and r is 1, and so the cosine would be -1. Do another one. Let's find, again, assuming the radius is 1, let's find the tangent of 450 degrees. So 450 is bigger than 360, so we know we're going to go all the way around once, and then we have to continue around, but how far? Well, if I take 450 and subtract 360, I get 90 degrees. So I end right back up here at 90 degrees. The point for radius equals 1, the coordinates for the point, radius equals 1, on the positive y-axis is 0 for x, 1 for y. And so the tangent of 450 equals y over x, but that's 1 over 0, and so tangent is undefined. One last one. Let's find the cotangent, 7 pi over 2. So again, where are we? Well, I know pi over 2 is 90 degrees. So if I want 7 pi over 2s, I'm going to do 1, 2, 3, 4, 5, 6, 7. I end up here on the negative y-axis. If radius equals 1, where am I? The negative y-axis, I'm at negative. For some reason, I want to write my coordinates backwards today. If I'm on the negative y-axis, x is 0 and y is -1. And so the cotangent of 7 pi over 2 is, well, cotan is the inverse of tan, and so that's x over y. X is 0, y is -1, and so 0 is the cotangent of 7 pi over 2.